In this video, we're going to look at the same problem that we had looked at previously, which has a thin curved ring, cantilevered at this end, 1/4 of a ring, a straight line section, a load F applied. But in this case, rather than calculating the deflection of this structure to the left, we're going to calculate the upward deflection of this structure caused by the load F. Now, in order to do that, we would have to calculate an upward deflection, we have to have an upward load. So we're going to place a dummy load Q at the location where we want to calculate the upward deflection. Eventually, we'll set that load Q equal to 0, and we'll see what falls out for the upward deflection. Now, a method I showed you in class, whenever we're going to be looking at the interaction of dummy loads and actual loads, is to build a little table that shows the various sections of the piece. In this case, it's just the straight and the round section, and show the kind of energies that are dealt with when we look at the deflection because of the load F itself. And we already saw in the previous problem there was an axial and a bending. And then we add to the table any energies that are going to happen because of the load Q. In this case, there would be bending in the straight section because of Q, and there would be bending in the round section because of Q. But what we saw was we only get non-zero terms when we have the same piece in both sections. If we have a piece by itself that's unmatched here, this piece will depend on Q, but then when we set Q equal to 0, it'll totally disappear. This piece won't depend on Q at all, and when we take the partial with respect to Q, the partial will go to 0. So in either case, these two pieces would go to 0. This is the only term that we have. And so let's take a look at, in the round section, we will be writing the bending energy due to both Q and F. And the moment in the round section, as we saw before, based on F, is an FR1 minus cosine of theta. The moment in the round section at a location theta, because of the load Q, will have a moment arm from the dot here to the load Q that encompasses this piece, which is r sine of theta, the angle theta being here, but it also encompasses the entire distance, L. And so that moment is Q, the force, times r sine of theta plus L. And the partial of this entire moment with respect to Q is r sine of theta plus L. We'll now calculate, and at this point we can set Q equal to 0. When we set Q equal to 0, the only piece we have left in the moment is FR1 minus cosine of theta. Then we're going to write our deflection due to bending is going to be a 1 over EI. The moment, which when we set Q equal to 0, only has this piece left. The partial, which is here. Because it's a round piece, we'll replace dx with r d theta. We have the 1 over EI piece, and we'll integrate over the entire round section from 0 to pi over 2. And because we took our partial with respect to Q, this will give us our delta in the deflection of Q. Multiplying these things out, we're going to get an integral from 0 to pi over 2, pulling the F's and the R's and the E's and the I's out. We'll have this term, and this term, when we expand it out, is going to have a cosine term, it's going to have a sine term, and it's going to have a product of sine times cosine. I'm going to leave all of that additional integration work. My mouse is disappearing on me. Okay, I'm going to leave all that additional integration work to you, but we'll have to integrate each of those terms, and for each of those terms plug in the limits 0 to pi over 2. And what we get when that's all done is an FR squared over 2EI, times an R minus 2L plus pi times L. And that would be, again, the deflection at the end of this beam in the upward direction because of the load F that's been applied. Okay, the dummy load Q has been set equal to 0. That was just a tool to let us use Castigliano to get that upward deflection.